So the fourth sample problem that we're going to do is a vertical circle. So this would be an object that is going up and down. So maybe you have a rope with something on the top of it and you're just standing here swinging it up and down. And in this case, I have a ball that's on the end of a string. I have a certain mass that I'm going to say is that 0.56 kilograms, and the string has a radius of 1.5 meters. Now, what we have to be careful on a vertical problem is where are they talking about on the problem? Because if you think about it, each place of the circle is going to have a different diagram. That's a horrid circle. I'm going to draw my circle just a smidge smaller. Not like that's any better, but since this is asking for 12 o'clock, then technically my force diagram is up here. I would have the force of gravity pulling it towards the center. I would also have the tension of the string that's pulling it downward. Now think about if I were talking about 3 or 9 o'clock, then I'm going to have, again, the tension of the string pulling inward, the tension of the spring pulling inward, but at both of those, won't my gravity be pulling in a different direction? It'll be pulling straight down. And when I look at the bottom of the loop, then aren't I going to have gravity pulling down and tension pulling up? So notice that each one of those different positions are going to have a different force diagram, which is going to play the math out slightly different. And then imagine how horrid this problem would be if we talk about it somewhere in the middle there, where like gravity is pulling this way and the tension is pulling this way, and then we're running into angles and we have to talk about the different components. It just becomes a nightmare. Now, all that to go back to then, since we're at 12 o'clock, we can take and look at that and say, I don't need to know this side one or this side one or this side one. I only need to know what the force diagram is at the top here when it's at 12 o'clock. So I have the two forces that are pulling it towards the center of the circle that is going downward that way. Now, what's the minimum speed at the top to maintain a circular motion? The key to that idea is that if I'm looking at minimum speed, then doesn't that mean that the ball is just going to barely go over the top? And when it does, then the string goes slack and there is no tension in the string. So if I'm talking about this ball going in a circle, F equals mv squared over r, typically at the top here, I'm going to have that tension plus the force of gravity is equal to mv squared over r. But if there is no tension now, then I'm just left with gravity is what's keeping it going around the circle and going over that. So the force of gravity, remember, we'll do is mg, mv squared over r. Our masses cancel out. And again, this should start looking familiar to you. Don't we end up with a very similar equation or the same equation that we had in the last sample problem where we have the square root of r times g is going to be our velocity. So the square root of 1.5 times 9.8, and that gives us a value of 3.83 meters per second. So that's how fast it can go over the top without actually falling downward. If the ball has a velocity of 14 meters per second at the bottom of the circle, so notice we're talking about a different part of the circle. So again, I'm going to have to look at the bottom part here where I'm going to have the force of gravity going down. I'm going to have the tension going up and complete my circle there. What is the tension in the string? So if I talk through this idea back over here again, I'm going to have the centripetal force, or the sum of all the forces, equals mv squared over r. Because it's going in the circle, I can say my tension is greater than the force of gravity. So tension minus gravity, the forces pulling toward the center will make positive. The ones going away from the center will make negative, equals mv squared over r. I'm looking for the tension, so I'm going to add the force of gravity to the other side. So you can conceptually think through, isn't the tension going to have to, 1, overcome the weight of the ball, and then 2, add enough to pull it towards the center of the circle? So we're adding the two of those together. Then I can plug numbers in. So 0.56 times a velocity, that is 14. So velocity squared divided by the radius, 1.5, plus 0.56 times 9.8. And then put that in your calculator, and you should end up with a tension of 78.7 newtons. So that's how much the tensile strength of the string has to be, otherwise the string is going to snap. If we have 100 Newton tensile strength of string, then the string won't have an issue. You now turn the string and rotate the ball horizontally above your head. So this would be a case where you're standing there spinning it this way. If the string has a tensile strength of 25 newtons, how fast can you rotate the ball? So remember the string, that tensile strength is what's pulling it towards the center of the circle. We're going to have to assume that it's horizontally, even though we know that it would sag just a little bit from that. But we can do F equals mv squared over r again, plug in our tension value is what we're looking for. I'm sorry, that's our tensile strength, mv squared over r, and then plug that in, the 25 equals the 0.56 times the v squared over the radius 1.5, and then solve for v. So when we solve for v, we end up with a velocity of 8.18 meters per second. So that's the fastest that you could swing that, 8.18 meters per second, without the string breaking because of the strength of the string. So again, this is the fourth problem that we've done. We did a conic pendulum, we did a banked curve pendulum, we did a friction pendulum, not a pendulum, and now the banked curve wasn't a pendulum either. So we did a conic pendulum, a banked curve, and a friction where a road is driving around a corner, maybe at a stop sign or a stoplight. And then this one is a vertical circle problem where you have an object that is spinning up and downward in that direction.